So it's my privilege to introduce Steve Chien. Steve is a pioneer in the area of automated planning and scheduling for space. He earned his bachelor's, his master's degree, and his PhD from the University of Illinois. He's currently a senior research scientist and group supervisor at JPL. And he's been working on deploying as well as research and development for planning and scheduling systems in space for about 20 years. He's deployed systems for Earth-based spacecraft, both on the ground and on board the spacecraft, also rovers at Mars, as well as aircraft campaigns, and of course, as we're in our context here, in underwater vehicles. And pretty soon he'll be having a system on his CubeSat. Steve.
Okay, so interestingly enough, coincidentally, my talk is mainly going to be joining together Yi's talk and the last talk. So I'm going to be talking about how space measurements and in situ measurements can be combined. Unfortunately, I'm going to be talking mostly on work that's been done in combining it in domains other than oceanography, but just at the very end, I'll touch on how these can be done in oceanography. So these are actually some of our collaborators in some of the other science disciplines we've been looking at. So the fundamental theme of my talk is on what I'm going to be calling adaptive sensing. And what I mean by adaptive sensing is you have some network of sensors with very many different modalities, complementary methods of measurement. Some are in situ, some are space. And how can you combine these in the appropriate way to get the best scientific measurements? And there are going to be two recurring themes that you're going to hear about here. The first is, since I'm an autonomy guy, we're going to talk about how far we've been able to push everything autonomously, and I'm going to give you some examples of how far we've been able to do that. And so the first thing is, how can we automatically interpret the data to go from low-level or raw data to the higher-level conclusions that we need to make different decisions? And then the second thing is, how can we, what is the state of the art? What have we been able to do in space vehicles and some of these other vehicles to automatically task, redirect, reallocate sensors? And then there's a wide range of sensors that we've applied these to. So obviously, if you have a mobile sensor, you have to worry about where it's going to go next. And AUV is the best example of where you have the greatest challenges, because you have to decide where to go next, how to coordinate with other assets. But in fact, the largest number of in situ sensors that we've integrated with are in fact not mobile. So then there's still other degrees of freedom you want to talk about. How much data do you send? How do you use those to trigger other sensors? And so on. All of this, as was mentioned in one of the earlier talks, apply to all kinds of different sensing: space, air, marine, ground, as well as a wide number of science applications, and we're going to see quite a bit of that. I'm going to be talking mostly about the two areas where we've been applying them most: hydrology and volcanology. So flooding is actually the most costly natural disaster in both humanitarian and dollar terms. And we have active campaigns going on, for example, tracking the flooding that's going on in Southeast Asia right now as we speak. Volcanology is another very important science discipline here. And lots of people have their lives threatened. And then also, economic damages from volcanism are quite extensive. In fact, multiple billions of dollars, just as a lower estimate for the Eyjafjallajökull eruption in Iceland. So what do I mean by adaptive sensing? So I'm going to start with the simplest possible example. This is an experiment we did actually with Arizona State in the 2003 range. And the idea here is we wanted to track the edge of the North Polar ice cap in greater detail. And so what we did is we linked together two systems. The first is DMSP, which has this particular thermal sensor that in one single day's data gives us a coarse measurement of the extent of the polar ice cap. But this is only at a kilometers per pixel resolution. And what we did is we tied this together with the satellite that we had control of, EO1, and we actually used this to autonomously retarget on the areas of greatest change in this, okay? And so the idea here is we're going from a kilometer scale measurement to a tens of meters scale measurement by focusing on the areas of greatest change here automatically with nobody in the loop. So that's a very simple example of the kind of thing that you want to do with adaptive sensing. Another example is tracking of wildfires. There are a number of systems globally that can track all of the thermal emissions. In fact, you referred to some of these. MODIS is the longest standing one. There's a system called Wildfire, which was built by Chris Justice and his team at the University of Maryland. And for over 10 years now, we've integrated this with a series of point-and-shoot Earth-observing sensors to allow us to dynamically detect the extent of these largest fires, triage them based on priorities, and target these point-and-shoot sensors. Again, we're going to see as a common theme here, EO1 in doing this. And in fact, we can automatically downlink that data at priority and derive products from it and automatically deliver that to responders, in some cases in the field. This, of course, is a great example because this is just behind JPL and about half a kilometer from my house. So, of course, we're very interested. So the central theme here is we automatically detect the larger scale areas and we direct the higher resolution sensors to track, observe, and deliver the end products that the scientists are interested in or the applications people. This is another example. This is flooding in Southeast Asia in the 2011-12 flooding season. This is the dry, and this is the flooded. At the peak of the flooding, you can see here, for example, that the Chao Phraya River here around Bangkok is heavily flooded. And then also here, the Chien and the Mun rivers and leading into the Mekong area. This area of the delta in the southern area of Vietnam is pretty much completely inundated here. And so what we do is we automatically detect the flooded regions of interest. We direct narrow field of view, higher spatial resolution instruments automatically to derive we downlink this data. We automatically derive the end user products. This is the raw image. This is actually a machine learning support vector machine classified surface water extent map. And then actually from this, we deliver to NGOs like the World Bank a product that enables them to look at a particular pixel on the ground and estimate the amount of time that it was underwater and the depth underwater, because that's a very good proxy of the damage to that site. So again, here we go from 250 meters per pixel to 2 meters per pixel. And the subsequent launch of WorldView 3, which is upcoming, will enable us to even further enhance this kind of response. And then volcano monitoring. Volcanoes erupt all the time with very little warning. This is some imagery from the Chien. This is a picture of the Chien volcano in Chile. And again, we automatically detect active volcanoes. In most cases, these are actually known sites. And then we direct narrow field of view, higher spectral resolution, higher spatial resolution sensors. And then we automatically derive the user products and deliver them to the authorities that are actually monitoring those volcanoes. So just to give you an example of how this is actually going on as we speak, this is actually a several-day-old acquisition. You can see here that EO1 actually acquired this just Saturday, and it's delivered this product. This product is also delivered to our collaborators in Thailand. This is an example of an alert that's processed by our collaborators in Ecuador of the Tungarahua volcano, which is also triggering subsequent observations and product delivery. So what's the underlying technology and overall scheme behind all of this? The idea here is that we have automatic detection, and this uses a number of satellite observing systems. MODIS is a great example because it hits every spot on the planet at least twice a day, twice a day and day and twice a day at night. And if you're in a polar location, you get even better. What are the potential data sources that are available, and what are the different assets we can direct towards that? What are the products? We need to update different modeling. I'm going to try and touch on that a little bit more because in the oceanographic context, the modeling is central to all of this. And then what are the end data products and how do you deliver them automatically? So that's the overall scheme of what we're trying to do. And then there's a series of mostly computer science information technologies here. We have workflows that kick off automatic data interpretation. We have some machine learning here. We have automatic planning that involves replanning tasking different spacecraft. We have to compute the overflights to figure out how to task them. We can reconfigure in-situ sensors. I'll give you an example of that. We actually generate these different products in the flooding example, surface water extent or depth maps, burn severity maps in the wildfire context. And then there are different methods that we use to automatically deliver these to the end users, because in a lot of cases, these data products are actually quite large. But the overall Sensorweb paradigm here is that we have all of these sensors, we have some detection process, we have some response process, which links up with some kind of model that we have, and then on the side we generate these different products. So based on the results of the detection in the model, we may deliver alerts to different people, and we may deliver different science products. And as we can see, this is purposely ridiculously high level, because you can see that this fits a crazy number of science disciplines right here. So this is an example of some of the work that we've done just with the EO1 satellite. These are all of the acquisitions that we've taken that are driven in a heat map here, including some oceanographic deployments such as the Monterey Bay 2008 deployment, flood tracking, including we have ongoing campaigns in Namibia and in Thailand, as well as one in Australia in 2009. And then a number of ongoing volcano campaigns that we have, including Mount Erebus, Iceland, and a number of other active volcanoes. We have another one, actually, that's not here on the map, that's ongoing with Etna and Stromboli and Vulcan off the Italian coast. We have actually a wide range of in-situ sensors that we've integrated with. These are mostly volcano observatory sites. For example, Iceland is very heavily instrumented with over 100 sensors, the Hawaiian Volcano Observatory, the Cascade Volcano Observatory, Mount Etna. There's instrumentation in Namibia that we've linked into, in Thailand, and then also in Ecuador and Chile. So what's our fundamental approach that we're advocating in linking all these together? We've fundamentally taken an agent-oriented approach where each set of assets hierarchically organizes into both, let's say, one externally exposed agent, and then plus the individual assets within that also have some aspects of autonomy. So it's something that's been called nested autonomy. It's something that's been called hierarchical autonomy. And the idea here is that each asset, or each level, there's different levels of capabilities that the system would have to be what we would call the most capable agent. So there would be some ability to do automatic interpretation to detect events from the raw data. There's a mission planner to determine if that asset can respond, should respond according to its behavioral policies that have been designed in the overall system. There's an execution system that allows these plans to be, to survive contact with reality. And then these assets all have to be architected in some sense in the global sensor web. Okay? If we have all of these assets that are architected with they're linked together without any sort of overarching principles, then basically you'll have anarchy, which is not that different from what we actually end up having. But in the long-term vision, what we would like to do is have these assets more brought together in a predefined, predetermined, planned fashion. So what's an example of one of these agents? Well, right now on board the EO1 spacecraft, we actually have onboard image processing that allows us to detect different kinds of events, ranging from volcanic activity to flooding, and more recently, specific hyperspectral signatures. We have a high-level planner on board that allows us to figure out, based on what our current observation schedule is, what new observations we could incorporate into our schedule, which ones conflict. We have an execution system that allows that plan to be converted into detailed commands for the spacecraft. And we have a lower level execution system as well that allows that system to interface with the actual hardware. And if you open up something like the autonomy system on board an AUV, for example, one of the systems that was mentioned before is the team led by Connor Rajan at Mbari, you'll see actually a very similar thing. You'll see a high-level autonomy, an execution system, and then you'll see some lower-level, more device driver support and behaviors. And so what does this enable us to do, this agent decomposition? It allows us to take an agent, to encapsulate it, and say things like, I can give that agent high-level observation requests with some priority, and it will go and prosecute them in concordance with its policies. That agent can also be relied upon to reasonably, intelligently, and responsibly issue alerts and issue observation requests. It can sort of act on its own and also detect and monitor phenomena of interest. And so, for example, this spacecraft on its own can determine when it's going to have another overflight and continue tracking this volcanic behavior. And then finally, the thing that's important in order to interface this with the external world, the real world, is it has to be able to analyze the data and assimilate that into these high-level event detections. Okay? And so with this generic building block, we can apply this across a wide range of sensors. And now I'm going to give you some examples of ways in which this has been done. One of the ways in which this has been done is in these non-mobile sensors that we deployed to Mount St. Helens. And each one of these sensors, these were deployed over the caldera in this configuration. And these sensors automatically network, and they all have a set of ability to measure things. They have a MEMS accelerometer, which is a seismographic instrument. One of the key pieces of information that they have is their network connectivity, which is a de facto an ash sensor, because the volcanic ash dramatically influences the ability of these to communicate with each other in the RF. They also had, let's see, they had an acoustic sensor. What else? There's a few other things. But the main focus here that I'm going to be talking about is the seismographic sensor, because that's the main data hog. And these sensors are all integrated in a hierarchical sense. So we had a set of these smart nodes that filter and summarize the data based on the local view. And then there's a bridge with a network-based autonomous system that actually allocates out the bandwidth to these based on the global view of the network, because one area of the network might be having a greater amount of seismic activity. This hierarchical node also communicated via a set of Open Geospatial Consortium web services, Sensor Observation Service, Sensor Alert Service, and Sensor Planning Service, to external nodes, including EO1 and others. And so this enabled us to do things like have an alert, a seismographic alert, filter up here and result in the tasking of the spacecraft, or have a thermal localization filter down here to allocate bandwidth within the sensors. Within the individual nodes, within node autonomy would allow us to do things like have this ring buffer where we collect the seismographic data at a very high data rate, detect events using this technique called RSAM, which is a measure of the amount of energy in the signal, and then determine this, what we call the seismic quality of service, which is the data allocation to that individual sensor, and then save that data with this pre-event buffer, and so that we transmit the data at the high resolution around the events, but at a low resolution the rest of the time. And so this is actually also showing how the triggering can go in both directions, up to space and back. Another thing that we do in these sensor webs is automatically interpret the data. This is actually a series of scenes from the Icelandic eruption at Eyjafjallajökull in May 2010. And what we do is we actually automatically process the data. This is sort of the raw thermal data. We automatically fit it to the black body radiation curves. And then we can actually estimate, using a model of the volcano, what's of most interest to the scientist, which is this mass effusion rate. And so this enables unique measurements. This is actually the amount of magma being emitted from the volcano, measured as a function of time across the evolution of the eruption. And this is fitted to different volcanological models, most notably the WAJ model that talks about the exponential increase in decay in the volcanic activity. So the key thing here is that this is purely space-based measurement, only using two instruments. What would be much better is if we could automatically develop this model, including the in-situ data, which was being collected, as well as all of the other satellite data that was being collected. We estimated there were over 60 instruments in the roughly 2 months of this eruption that theoretically could have been collecting infrared emissivity data on this. And so the idea is, how can we bring all of those together automatically in order to do that? And finally, the corroboration or actually automatic combination of the ground measurements would be critical as well. And so in the flooding arena, as I mentioned before, we go directly from the automatic detections using MODIS, and more recently we have automatic detection using in-situ instrumentation in a collaboration with the Hydroagro Informatics Institute in Thailand. And then from that, we actually task satellites like WorldView 2. And then this shows actually the training of the classifiers using support vector machines. And then the water volume estimation basically happens from finding the periphery of water bodies and corroborating that with the digital elevation map. And we do this with a range of sensors, and the commercial sensors turn out to be the ones that have the highest resolution. So this is from Iconos. This is from GeoEye. We also have data from Landsat and RadarSat that we can use to produce these products as well. And so we deliver all these products actually to the Thai authorities on a steady basis. And so literally we've delivered hundreds of these products over the last 3 flooding seasons. And so finally, I'm going to touch on how we use other mobile assets. So UAVSAR is a JPL NASA aerial platform that has a synthetic aperture radar that can develop both SAR and interferometric products. And basically, we've integrated this, and in several test flights, not in an operational mode like the earlier things we talked about, we've demonstrated that that could be tasked just as another asset in the sensor web. And now I'm going to just touch a little bit about what this means in oceanography and then finish up here before Becky shoos me off. So as all of you in here know, of course, we have this confluence of ocean models, in situ assets in both space and, let's say, CODAR as a broad-scale measurement. And the key thing here is that the space data generally only gives you the surface, but it gives you the broadest spatial coverage. The in-situ data gives you horrible spatial coverage, but it gives you the coverage at depth, and plus you can direct it. So moving forward, what we would like to do is take these different models and actually use the modeling information, and much more importantly, the uncertainty information in the model to automatically drive the assets. Yi alluded earlier to a deployment we did off the Mid-Atlantic Bight in 2009, but in this case, again, people were in the loop looking at where the assets were, where we could send them, using automated tools to figure out where we could send them and what was the likelihood of getting there, but still fundamentally people were in the loop. And I think one of the things that we need to achieve this persistence that's been one of the central themes here is we need the ability to have these assets automatically sent places regardless of when it happened. So when the Eyjafjallajökull eruption happened, it happened roughly at midnight local time on a Saturday in California time, and by the time our lead volcanologist scientist heard about it, Sunday morning he logged in online and saw that already the system had retasked and acquired 2 images. That's what we fundamentally want. So just to touch on this finally, this is an example of automatic heuristic path planning for a single AUV, but we have multi-AUV models, which is using a path planning based on what we call reward gathering of uncertainty in a ROMS model. So if ROMS is operated in an ensemble mode, it has an uncertainty estimate, and we're trying to drive the in-situ instrumentation to the area where there's greatest uncertainty. Now, what we'd actually like to do is sample the places that would drive some measure of overall uncertainty down the furthest, which, of course, is different from sampling the area with greatest uncertainty. In order to really do that, you have to know what the covariance is, you direct the sensing, you fold in the new measurements, and continuously repeat that. So this is my last slide. So just to summarize, adaptive sensing is being used a fair amount in the space context in Earth sciences. And the key elements here are automatic interpretation of the data, both local and global autonomous response. And particularly in the context of the Ocean Observatories Initiative, we looked at local response in terms of what an individual asset might do, like a single AUV. And then the global response, or regional response, is more what a shore-based planner would do in directing the in situ assets to the right area. And then finally, automatic alert generation, because you want to keep the science and operations team in the loop. I want to emphasize that a lot of these technologies have been in operational use for on the order of a decade. However, what's fundamentally different between that prior work and this work, the work that we're trying to do in this workshop, is that we haven't really delved into detailed integration of the modeling with the autonomy, and also we're in a different world here with the total spatio-temporal immersion here in dealing with that and how that integrates with everything. With that, thank you.